BSc Chemistry, Electronic Spectra, presented by Dr. Giridhar M., Assistant Professor of Chemistry, Department of Collegiate Education. So let us start with the contents, electronic spectra. So in this session, we will be studying potential energy curves for bonding and anti-bonding molecular orbitals, band theory. Potential energy curves for bonding and anti-bonding molecular orbital. So according to molecular orbital theory, atomic orbitals combine to form molecular orbitals. So the total number of molecular orbitals formed will always be equal to total number of atomic orbitals offered by the bonding species. For example, if we take hydrogen atom, two hydrogen atom combine to form hydrogen. So each hydrogen atom contains one electron, that is one atomic orbital. So therefore two atomic orbitals are there, and these two atomic orbitals combine to form two molecular orbitals. So there exist different types of molecular orbital: bonding molecular orbital, anti-bonding molecular orbital, and non-bonding molecular orbital. So of this, anti-bonding molecular orbital will always have higher energy than the parent orbital, whereas bonding molecular orbital will have lower energy than parent orbital. So when atomic orbitals combine, say for example two atomic orbitals combine, then two molecular orbital is formed. One will form bonding molecular orbital lower in energy, and another one will form anti-bonding molecular orbital which is higher in energy. So the electrons are filled into molecular orbital in the increasing order of orbital energy, from the orbital with lowest energy to the orbital with highest energy. The most effective combination of atomic orbitals for the formation of molecular orbital will occur when the combination of atomic orbital have similar energies. So that means those atomic orbitals which have same energy will combine to give molecular orbitals. The potential energy curves for bonding and anti-bonding molecular orbital can be studied by plotting a graph of energy level splitting on the average distance between atoms. So if two hydrogen atoms are brought together, two levels are formed. So that is one bonding and one anti-bonding. If four hydrogen atoms are brought together, four levels are formed. Okay, that is four possible symmetries, gives rise to four possible symmetries. A single sine wave hump in each well, alternating up and down, and so on. So that means if these atomic orbitals in the form of wave, okay, when two waves combine, that can give rise to four types of waves. Okay, so in one of the wave it will be hump like this, and in second wave like this, third wave will be okay, different types of combination of four waves gives four molecular orbital in this case. So in the limit of very large number n of atoms, so that means when large number of atoms are present, we expect a spread of nearly continuous bands of electronic energy levels. So in a solid, each of these bands is known as energy band. The allowed state of energy and wave number are still technically quantized, but for large number of atoms, these states are close together and that they are considered to be continuous or in continuum. So let us see here. So when two hydrogen atoms are formed, so we see that this is anti-bonding, okay, anti-bonding, and this is bonding molecular orbital, which are in the form of wave. And when four hydrogen is combined, then this is anti-bonding, this is bonding, okay, two bonding and two anti-bonding molecular orbitals are formed. And when large number of hydrogen atoms are combined, So all this the bands will give rise to a form of band. Okay, so this will form a band. So this is potential energy curve, okay, for n number of hydrogen atom, for the combination of n number of hydrogen atoms. So these are given: A for 2 atoms, B for 4 atoms, and C for large number of atoms. So for large number of electrons, a continuous band of energy is produced. Okay. So next we will move to band theory. When large number of lithium atoms combine, so what happens? The combination of 2s orbitals give bonding molecular orbital which form valence band, and antibonding molecular orbital form conduction band. So that is when large number of lithium atoms combine. So all the 2s orbitals combine to give bonding molecular orbital and antibonding molecular orbital and bonding molecular orbital. So these, since large number of lithium atoms are there, this bonding molecular orbital, they form a band. Similarly, antibonding molecular orbital will form a band, and this bonding molecular orbital is also called as valence band, whereas antibonding molecular orbital is called as conduction band. So we can observe here, when large number of lithium atoms combine, 2s orbital will form valence band, 2s star orbitals will form conduction band, and this is empty p orbital which is present in the lithium atom. So we can observe here 2s1 of lithium atom combined to form 2s bonding molecular orbital which is fixed, which is having filled electrons, and 2s antibonding orbitals which is empty. The basic difference between conductors, semiconductor, insulators lies in the number of free electrons present in the material. The difference can be best understood on the basis of band theory of solids. So if you see here, so this is the band gap between valence band and conduction band, which decides whether the material will form insulator, semiconductor, or conductors. When the band gap is very large, it is considered as insulator. When the band gap is intermediate between that of conductors and insulators, it will form semiconductor, and in case of semiconductor, the valence band and conduction band overlap. That is, band gap is either very small or the two bands will overlap. So conductors, based on the band theory of solids, we can define conductors. Since band gap is very small, electrons easily jump from conduction band to valence band. Only small amount of energy is sufficient to allow electrons to move within band. This movement of electron within conduction band constitute electrical conduction. In some metallic conductors, valence band and conduction band overlap. So this is what, when the it can overlap, or band gap can be very small, so electron can easily move from valence band to conduction band, and therefore we see conduction in conductors, electrical conduction in conductors. So next, insulators. In an insulator, valence band is full and band gap is very large. Thus, it will take great deal of energy to make an electron jump the energy gap and to cause insulator to break down. The breakdown does not occur even at high temperature or under very large electric fields. So for example, rubber is an example for insulator. Since the band gap is very large, electron cannot jump from valence band to conduction band, hence there will be no conduction of electricity, and therefore the material acts as insulator. So next we will move to semiconductors. These are materials which have conductivity between conductors and insulators. There are two types of semiconductors. One is semiconductor can be pure, that is, they are called as intrinsic semiconductors, and examples are silicon, germanium. And second one, it is called doped. Okay, so these semiconductors are doped and they are called extrinsic semiconductors, such as gallium arsenide or gallium arsenide, selenium, cadmium selenide, etc. So here gallium, okay, arsenide is doped into gallium. Similarly, selenium is doped into cadmium. So let us move to intrinsic semiconductor. An intrinsic semiconductor is made up of pure substance, that is, no impurity has been added to it. The best known intrinsic semiconductors are silicon and germanium. So in an intrinsic semiconductor, the valence band is full and conduction band is empty at very low temperature. The band gap, e.g., the band gap between the two bands is, however, so small that electrons can jump across it by addition of small amount of thermal energy, which is Kb by T. Okay, where Kb is Boltzmann constant and T is temperature in Kelvin. Only heating the materials results in electrical conduction. The electrical conductivity increases with increase in temperature, since more and more electrons are liberated with increase in temperature. So this is about intrinsic semiconductor. So next we will move to extrinsic semiconductor. An extrinsic semiconductor is a semiconductor doped by a specific impurity which is able to deeply modify its electrical properties, making it suitable for electrical applications like diodes, transistors, etc., or optoelectronic applications, that is light emitters and detectors. So here a small amount of impurity is doped in pure semiconductor material. So there are two types of extrinsic semiconductor. So one is P type, P for positive. A hole has been added through doping of group 3 element to group 4 element. And N type semiconductor, N for negative. So an extra electron has been added through doping with group 4 element to the group 5 element to the group 4 element. So next we will move to N type semiconductor. So N type semiconductors are created by doping an intrinsic semiconductor with an electron donor element during manufacture. So here electron donor element is doped into pure semiconductor. So the term N comes from negative charge of electron. In N-type semiconductor, electrons are majority carriers and holes are minority carriers. So here electrons are the main carriers of electricity. A common dopant for N-type silicon is phosphorus or arsenium. So here phosphorus or arsenium is doped into silicon to create N-type semiconductor. In an N-type semiconductor, the Fermi level is greater than that of intrinsic semiconductor and lies closer to the conduction band than the valence band. So next we will move to P-type semiconductor. P-type semiconductor are created by doping an intrinsic semiconductor with an electron acceptor element during manufacture. Okay, so intrinsic semiconductor is doped with electron acceptor element. The term P-type refers to the positive charge or a hole. The P-type semiconductor, in P-type semiconductor, holes are majority carriers and electrons are the minority carriers. A common P-type dopant for silicon is boron or gallium. So here boron or gallium is doped into silicon to create P-type semiconductor. For P-type semiconductor, the Fermi level is below the intrinsic Fermi level and lies closer to the valence band than the conduction band. So this is about P-type semiconductor. So reference. Thank you.